In this video lesson, we will look at the introductory production program example that I already solved in Excel Solver, this time solving it in Python using PuLP and the default solvers in PuLP. The problem consists of having three different product types that can be produced on a single machine, and the single machine has a defined capacity that is specified in amounts of available minutes. Different products have different processing times and different profit margins, and the objective is to maximize the profit margin. We have to consider that there is a forecasted market demand, and if we produce more than is forecasted to be the demand, this will not generate additional profit. So this is the production program problem that I already solved in Excel Solver and that served as an introduction to Excel Solver. And now we will solve the same problem using Python. We will model it with PuLP, and we will use the default solvers in PuLP to solve this problem. So the first thing we have to do is to import PuLP, and it supports pip install, so if you have not installed PuLP yet, go ahead and install it using pip install. And that is actually the only thing that we need in this case. We then need to set up the relevant input data to a problem. This is the known information that is available to us. The input data in this case are the profit margins for the various products. So I will define a vector here for the profit margins for product A, B, and C, being $2, $4, and $3. The other known information that is available to us is the forecasted market demand. Here, containing the forecasted demand for product A, product B, and product C. And lastly, in terms of a vector, we have another vector of known information, which is the processing time for each product. So again, I will put an array here containing or a list here containing the processing times for product A, product B, and product C. Last parameter that is available to us in terms of input data is the machine capacity, which is 1,200 minutes. After we defined all of the input data, which is the information that is available to us, the information that is known at the beginning of solving the problem, we have to specify the decision variables. And the decision variables are the variables that we can adjust using a solver so that we get an optimal outcome. And in this case, the decision variables are the quantities produced of product A, B, and C. And we will define them now using PuLP. For this I will create another vector that will contain the decision variables. And using the PuLP framework, we can use the LP variable class to define decision variables. In this case, we want to set up a dictionary containing the three decision variables, which would be the quantity to produce of product A, the quantity to produce of product B, and the quantity to produce of product C. So for this I use a decision variable dictionary, and you can see here the parameters that I can configure when defining a decision variable dictionary using PuLP. So first of all, we can give this a name. This X, which will basically be the name of the decision variable. And in terms of indices, I will just use the indices 0 for product A, index 1 for product B, and index 2 for product C. This is how you can define the indices. So now PuLP knows that we're defining three decision variables in the form of a dictionary. The dictionary has the name X, and well, this decision variable is basically a dictionary. It contains three indices. What we have to define is the category. The category specifies to the type of decision variable. In this case, it is an integer, since we can only produce entire products. So decision variable is an integer decision variable. What we can also do is we can define a lower bound to ensure non-negativity. So I will make use of that and set it to 0, just to show you how you can define a lower bound with regards to decision variable in PuLP. And that is it. So here we defined our pre-index decision variable for the quantities to produce of product A, B, and C. Next, we now have to define the model, set up the model. So the first thing we will do is to create the model. For this, we will create an instance of a PuLP linear programming model, since we are going to use we will use linear programming to solve this problem. So I call the PuLP framework and I define this problem as an LP problem. So I'm creating an instance of the LP problem class. Again, here there are several parameters that I could configure. What I want to do is I want to give it a name, and I will call this production. Or we could also call it production plan problem. And then we can use the sense parameter to define whether this is a minimization or maximization problem. In this case, we want to maximize the profit margin, so we want to make sure that this is recognized as a maximized problem. So there we go. We set up or created the problem here and specified it as a linear programming maximization problem. Next, we have to add to this problem the objective function. And after we set up the objective function, we also have to add the constraint or the constraints. And once we did these two steps, we can go ahead and solve the problem. But let's first define the objective. And the way to do this using PuLP syntax is to add objective functions. Like this. Again, I call the PuLP framework and I add a function of the type LP sum. So this is a linear sum. And here I will define the objective function. I show you here how to do that using PuLP syntax. Specify it, and then I will go ahead and expand. So what this function takes is a list of values, and then it sums up all the values in this list. And each value in this list is going to be, basically this list will contain the sum product, which would be the equivalent in Excel. So we're summing up the profit margin of the first product with the production quantity of the first product. And remember, this is our decision variable, so this is the value that we can actually set using the solver. And we will have one value for each product here. And in sum, this will be the total profit margin. Next, we have to define the constraints. In this case, they're, depending on how you want to look at it, 4 constraints. The first constraint is that the machine capacity is respected, so we cannot produce more than 1,200 minutes of machine capacity or machine time. And constraints 2, 3, and 4 would be that the production quantity of product A, B, and C is not greater than the forecasted market demand for the respective product. So I will go ahead and add these constraints now. First, I will add the constraint of machine capacity. And again, I'm using PuLP syntax, so I'm going to use this plus equal operator to add another function to this problem. And again, I'm going to call the PuLP framework, and I'm going to use the sum. And I will add another list here containing some other values, namely the production quantity of each product multiplied with the processing time of each product. So this sum product of the processing times and the production quantities will result in the total utilized machine capacity. And in order for PuLP to recognize this as a constraint, I have to add a direction of the constraint at the end. In this case, we want this to be smaller than or equal to the machine capacity, which was parameter C. And now PuLP knows that there's a constraint to this linear problem, which is that the sum product of production quantities cannot be greater than total machine capacity. And now I want to add three more constraints, which is that the production quantity of product A, the production quantity of product B, and lastly the production quantity of product C is not greater than forecasted market demand. And I could manually write each constraint here like this, and then similar to above, add constraint 2, 3, and 4. But I can also just use loop for them. So I'm just gonna create a loop here that will add three constraints. Let me call this and I will add three constraints, again using a linear sum to specify the constraint functions. In this case, I don't need it. I can just say that the respective production quantity has to be smaller than or equal to the forecasted demand for the respect. This is another example of specifying constraints. Here I used linear sums to specify some products, but that's because this was the nature of the objective function, this was the nature of the constraint function. In this case, I don't need to use any linear sum, since I'm just setting the upper limit for each variable, so to say. There's another way of doing something like this. When specifying a decision variable, you can also set the upper bound, as you can see here with the up bound parameter. So whichever way is easiest for you, you can use these two options. But I, in this case, prefer to put it into the constraint section to make it more clear that this is a constraint for the respective product types. And that is basically it. We set up the input data here. We could also have read this input data from a CSV file or from an Excel file or from a database. We defined the decision variables. In this case, we used the dictionary for defining, so to say, one decision variable with three indices referring to product A, B, and C. The decision variable is the production quantity of each product type, we created a PuLP problem. We used the LP problem class to define this as a linear optimization problem. We gave this optimization problem, this instance of an optimization problem, name, and we specified that this is a maximization problem. And we then added objective functions and constraint functions, specified all the constraints. Now we can go ahead and solve the problem. If we want to solve this problem that we already set up and added objective functions and constraints to, we can just take the instance and call the solve method. And this will solve the problem. But we also want to see the result. So we will add some code here that outputs the value, the optimal value of each decision variable, and also the total profit margin resulting from this. So what I will do is I will iterate over all decision variables added to this problem. In this case we have 3 decision variables. I will print their name and output to contain the variable name and then an equal sign and then the actual value. So this is how you could go about it. You could iterate over all the variables of this LP problem using PuLP syntax, and this instance of each decision variable will then have an attribute name, and it will have an attribute containing the value of the variable, referring to the solution. So what I'm outputting here is the optimal solution to the production quantity of prog A, B, and C. And lastly, what I wanted to see was the total profit. Add another print statement here, and now I want to add here the value of the objective function. So I can go about that like this. Using the PuLP framework, using the value function, I can forward the objective of a problem as an input parameter to the value function, and this will output the objective value. Now I can execute this model. I saved it as intro py. I'm already inside the dictionary, so I just call Python intro. And then you can see there is some output in the terminal referring to the optimization run and the solver used. You can see how much time was required to solve the problem, and you can see the optimal objective value as part of the default solver output, but the actual custom solution output that we added to the code is the part down here. And you can see the optimal production quantity of prog A is 66 units. The optimal production quantity of prog B is 50 units, and then we will produce 400 units of prog C, resulting in a total profit of $1,532.